Today our topic is theory of bending. In the previous class, we discussed the types of beams, the beam definition, the types of loading on the beam, then how to find the support reactions for different types of loads. Okay. Now, today class we'll see actually what is the theory of bending and how to find the bending stress in a beam when beams are subjected to complex loading. So the Euler beam theory is classified into one, long beam theory. The other one is short beam theory. So in the long beam theory, the bending moment that is acting on the beam will be constant. Okay. Whereas in the short beam theory, the shear force will be more dominant, so which is not equal to 0. In the even, the bending moment also will present, which is not equal to 0. In the long beam theory, bending moment is constant, but the shear force is 0. So that means pure moment. This is a beam subjected to pure moment. Okay. So where the bending moment is constant and its shear force is 0, this is called a simple beam theory. Simple beam theory. This is the theory proposed. Then in the beam theory, both the shear force, bending moment are not equal to 0. In the short beam theory, the shear force will be more predominant compared to the bending moment. Okay. Generally, these are like a short blocks. Examples are here. Short blocks, or simply you can say blocks, where the shear force will be more dominant, the bending moment will be neglected. In the long beam theory, bending moment is constant and shear force is 0. In the beam theory, the shear force and the bending moment both are not equal to 0. Both will present. Okay. Now, our topic will be confined to the beam theory given by Euler. So, first, Euler has taken a beam, then he has given some notations for the beam. Then, when the beam is subjected to a moment or a transverse loads, the beam undergoes bending. Okay. So, I will consider a beam. So, let us consider a simple supported beam, or we can say even cantilever also. We can connect. This is the beam. The beam will have a cross section. This is the cross section. Okay. Now this is the beam. So this is the top layer. Then the bottom one is the bottom layer. Like this, the beam will contain infinite number of horizontal layers. And the top layer will be under tension. The bottom layer will be under compression when this beam is subjected to bending moment M. Okay. Now, there is a layer at the center of the beam center of the beam, that layer is called neutral layer, which is unaffected by the bending moment. That layer is neutral layer. So, he said the beam contains infinite number of horizontal layers, out of which the top layer will be there, bottom layer will be there. When the beam is subjected to moment, the top layers will be under tension, bottom layers will be under compression for the moment direction shown in the figure. Okay. Suppose if you reverse the direction of the moment, the top layer will be under compression, bottom layer will be under tension. Okay. This is the first point made by the Euler. Then, the beam also contains infinite number of vertical cross sections. Say like this is one cross section, like this. Like this, the beam contains infinite number of vertical sections. Okay. Vertical sections. So, when the beam is subjected to moment, as shown in the figure, he said the beam undergoes perfect bending in the form of a circular arc. Okay. So, this will bend like this. The beam will bend like this, so that the cross section which remains vertical before loading also remains straight, but with respect to the initial position, this will undergo rotation by an angle theta. Okay. If this is the axis of the beam, this is beam axis. Okay. Generally, the vertical axis, this will be the load axis where we can apply the load on this in this direction. The axis which is perpendicular to the load axis and beam axis, where the cross section rotates. This is the point where the cross section rotates. Okay. This axis is called neutral axis. Okay. So, he said every beam will have a three axis. One is the load axis, other one is the beam axis, which is along the length of the beam. The third one is the neutral axis, which is perpendicular to the cross section. So, which is passing along the cross section, perpendicular to the load axis as well as beam axis. So, this is the assumption he made. Okay. Now, when you extend the tangents where the cross section undergoes rotation, when you extend the tangents will meet at a particular point. That point is called center of curvature. Okay. So, he assumed that the beam undergoes bending in the form of a perfect circular arc, and when you extend the tangent to the surfaces, the end surfaces, they will meet at a point called C, that is center of curvature. Center of curvature. Okay. Now, the distance measured from the center of curvature to the center of the beam axis, that distance is called radius of curvature. So, here R is the radius of curvature. Right. So, here if you take a small elemental thickness of the beam, a distance equal to x from any one end, let the thickness of this element is dx. Across the cross section, I will draw the cross section here. This is the cross section. So that this is the neutral axis, which is perpendicular to the beam axis and load axis. So this is neutral axis. Okay. So here on the cross section, somewhere here, because when I extend this, it will be, the beam will bend like this. Okay. So if you see this cross section will be like this. So when you take a small elemental strip here, at distance equal to y of thickness dy. Okay. So that means this is the beam before loading. This is the axis. So here I am showing only now like the front view of the beam. I am taking a small strip here. Say let the length of the strip is AB here, one above the like neutral axis or the axis of the beam, one on the beam axis, another one below the axis. When this is subjected to bending, we observe that the beam bends in the form of a curve. Okay. The element AB will stretch, whereas the element, this is the CD element. Since this is on the like neutral layer, it will not be unaffected. It will be like unaffected. The bottom layer will be under compression. This is EF. Okay. So that see, when this bends like this, okay, this is the initial position. Say this is the axis. This top layer will stretch here. This layer will stretch by, say, like call it as a dash, B dash. Whereas this is the layer which is on the axis unaffected, C, D or C dash, D dash. The bottom one will undergo compression. Okay, this is C dash, D dash. So this distance we are calling as a Y. Okay. Got it? Now, when you apply the load within elastic limit, so this layer, the small element AB is stretching to A dash, B dash. Then Euler said if the load is applied within elastic limit, the stress induced because of the stretching, the stress is equal to E into strain, where strain is defined as change in length ratio to that of the initial length. What is the change in length? A dash, B dash final length minus AB initial length by AB the initial length. This is the strain within the element. Now when I extend this, I told you already this is the center of curvature will be somewhere. Now this distance is the radius of curvature. Suppose if this subtends a small angle d theta, right? Subtends small angle d theta. The arc length A dash B dash is given by, this is R plus this distance is Y. That is R plus Y into d theta minus AB. AB, see, before loading, AB is equal to CD is equal to EF. So that that AB will be equal to CD. But what is CD here? R into d theta by R d theta. So that when I expand this, this becomes Y by R. So the strain in the element because of the bending moment is given by Y by R. If you take the element below EF, this will be minus. Why? Because bottom layers will be under compression, where top layers will be under tension because of the moment. Okay. Now, whenever there is a strain, so we know the stress. The stress is equal to E into strain. That is E into Y by R. Then he established a relation sigma by Y, the stress, normal stress, by the distance from the neutral axis is equal to E by R. Okay. This is the relation between normal stress, distance, Young's modulus, and radius of curvature. Okay. Now, So when the stress is because of some elemental force, because try to apply some elemental force on this element so that the element will stretch to A dash B dash. Let there is a elemental force there. That elemental force delta F is equal to stress into the area, because this element, see here, this is the area where the stress is acting. So that this is dA, that is into dA. Okay. Now this is only acting on an element, but we can take this n number of elements across the cross section. So that the small element on this is the elemental moment delta M is defined as the elemental force into the perpendicular distance. Okay. But across the cross section, we are applying the total moment. So the total moment is given by integration of the elemental moment. Okay. So that the elemental moment delta F into Y. But what is delta F? Already we know that is stress into delta A into Y. That is the stress is given by E into Y by R into dA into Y. So that that is, we rearrange this equation, E by R into integration of Y square dA. So we know that the integration of Y square dA is nothing but the moment of inertia about x-axis or about neutral axis. Ix is Y square dA. That's what we can call as a I. Therefore, the moment applied M is equal to E by R into I. So when we rearrange this equation, we get M by I is equal to E by R. But in the previous relation, we got E by R is nothing but sigma by Y. So this is the equation given by Euler. This is the equation given by Euler. That's why this is called Euler equation of bending. Okay. Since the beam theory is also called as a flexure theory, this is also called as a flexure equation of bending. This is flexure equation of bending. Right? So, Euler derived this equation based upon three important assumptions. One is the top layers will be under compression tension, bottom layers will be under compression, or vice versa. That depends on the direction of the load. The second assumption he made is the cross sections of the beam remains straight before and after loading, but they undergoes rotation about an imaginary axis called neutral axis. Okay. The third point, the third assumption he made is he assumed that the beam is undergoing bending in the form of a perfect circular arc, so that we can apply the equation for the radius of curvature. Okay. Anyway, the fourth assumption is common for the entire subject. The load is within elastic limit and Hooke's law is applied. By making these assumptions, Euler arrived at this equation. Okay. Now, in this where M, in this equation, M is the applied bending moment. Applied bending moment. So, if you apply the transverse loads, because of the transverse load, we'll have a bending moment, where the load into perpendicular distance gives moment, where I is the area moment of inertia of the cross section, Y square dA. This is area moment of inertia. Okay. Then E is the Young's modulus of beam material, because we can use different materials in the engineering applications. Okay, mostly our theory is limited to only metals which are isotropic in nature, where the strength of the material is constant, so that Young's modulus will be constant. Then R is the radius of curvature. Okay. Then sigma is the bending stress, which will act perpendicular to the cross section. Because suppose this is the beam, when apply moment like this, the top layer will be under stretching. That means this cross section will rotate like this. If this is rotating, means some imaginary force is acting normal to the cross section, which will produce the stress. That stress is called normal stress. That this is also called as a normal stress, because bending stress is always normal stress. Or we can call it as a flexural stress, because in numericals they can give different names. Flexural stress. The unit will be Newton per mm square. Okay. And y is the distance from the neutral axis, above or below where we are finding the bending stress. Y distance from the neutral axis. Okay. Above or below. Okay. So that we can find the moment of inertia for a given cross section. We can find the bending stress. Okay. So this is the Euler equation of bending. Okay. Now let us see, find out the bending stress distribution across the cross section of the beam. Okay. Next. Bending stress distribution. Okay. Say, when the beam is subjected to bending moment, we got the equation M by I is equal to E by R is equal to sigma by Y. If you consider the first and last terms, sigma by Y is equal to M by I, where the bending stress sigma is given by M by I into Y. This is the equation for bending stress. See, if I consider a rectangular cross section, this is the rectangular cross section. Okay. This is the axis, neutral axis. This is the top layer. This is the bottom layer. Y on the neutral axis will be always 0. Say this cross section will have dimensions. Let B is the width of the section and D is the depth of the section. Okay. So that here Y will be plus D by 2, Y max. At the bottom it will be Y max, that is also minus D by 2. Because if you consider the top positive, bottom will be negative, or bottom positive, top will be negative. Because it depends on the direction of the load, only the stress direction will reverse. Okay. Now see here, when Y is equal to 0 on the neutral axis, what happens? Bending stress is 0. Okay. So most important point, that means on the neutral axis, bending stress is always 0. This is by default, you have to remember. Bending stress always 0. Okay. Now, when y is equal to, say, y max, y tends to y max. So the bending stress becomes maximum. That is, sigma max is equal to m by I into y max. So now for a rectangular section, we know that the moment of inertia is given by Vd cube by 12 and y max is given by d by 2. Okay. So sigma max is equal to m by I can write as a y max. Okay. This is m by z. Okay. Here replacing moment of inertia and maximum distance by one single parameter, that is z. Here z is called I by y max. This is the section modulus. Okay. This section modulus got some important significance here because we are truncating two geometrical parameters, moment of inertia and distance. Both are geometry only. So replacing by one single parameter called section modulus. For a rectangular section, I is Vd cube by 12 by y max is d by 2. Therefore, the section modulus for a rectangular section given as Vd square by 6. This is the section modulus. Okay. The section modulus indicates the geometric strength of the material. This indicates, you can say, the meaning. Indicates geometric strength of the material. Okay. See, for example, suppose say like this is the beam. This is the beam. Okay. When I hold it here, when I apply load like this, will bend very easily. Why? Because here, see, this is the B. The B is small, the B is more, and D is less. That's why the section modulus will be less. But if I orient the beam like this, in this direction, and apply load like this, in the direction of the load, the depth D is more and B is small. So if you increase the D and if you decrease the B value, section modulus will increase. When the section modulus increases, see here, when the section modulus increases, what happens? The bending stress will decrease. That means the material is like a stressed, like a at lower level. That means the life will be higher, or it can carry more load, we can say. That's why the section modulus indicates geometric strength of the material. Just by changing the orientation of the geometry, okay, we can increase the strength of the material. Say like this. Suppose this is the case 1. Say here, I am fixing this here. Okay, this is the beam, case 1. Apply the load here. Apply the load here, so that this becomes B, this becomes D, depth. In another case, same material, we are not changing the material, we are not changing the geometry. Okay. So fix the beam here. Okay. Now apply the load in this direction. Okay. Now this becomes a B, whereas this becomes D. Suppose this is case 1, this is case 2. Okay. So here sigma 1 is given by same moment is same, that is m by z1. In this case, sigma 2 is given by m by z2, where z1 is b1, this is d1, this is b2, this is d2, b1 d1 square by 6. Here z2 is b2 d2 square by 6. Okay, since we know that z2 is more than z1, okay, the stress sigma 2 will be less than sigma 1. Under the same loading conditions, same geometry, same material, we are not changing those things, so that the cost of the beam will be fixed. But simply if we change the direction of the loading, in the case 2 direction, the stress will be very much less compared to the case 1, so that this beam will be stronger and it can carry even more load also, or this life will be more, because the stress in the second beam is more than that of the first beam. Okay, that's why the section modulus indicates geometric strength of the material. Just by changing the geometry, we can actually increase the strength of the material, or we can increase the load carrying capacity of the beam. Okay, now let us see the bending stress distribution. Since here stress is equal to m by I into y, this is just like equation, our equation y is equal to m into x. So here the stress varies linearly with respect to the distance y, because m by I is constant for a given load and a given cross section. So that if you draw the bending stress distribution, for any stress distribution, always draw the reference line. This is the reference line, this is the axis. Here the bending stress is 0. When y is maximum, stress will be maximum, that is at a top layer. If it is a tension, show like this, tension. Now, this decreases linearly and becomes 0 on the neutral axis. At the bottom, it is actually compression. Compression means negative, so opposite direction. Again, it will decrease linearly here. Okay, so that the bending stress distribution will be linear like this. So it is a triangular variation. This is the stress distribution on a rectangular section. Okay, if it is like a 3-dimensional, because if our beam is like this, okay, on this also, this is the neutral axis. Okay, this is the neutral axis. Let us see the stress distribution here. So top we will have a tension. So this will vary uniformly like this, and it will decrease up to this. At the bottom, it will be like a compression. Compression means in this direction. This is the stress in an isometric view. So that see, it will decrease. Okay, in a 3-dimensional form, the stress distribution will be across the width of the section. The stress will be constant at a particular depth. Okay, anywhere, suppose at the depth here, here, or here, or here, anywhere, the stress will be constant. Again, if you take some location here, here, at a particular depth, the stress will be constant across the width of the section. Okay, so because the analytical methods always gives approximate answers. Okay, this theory is based upon so many assumptions. That's why we are taking as a uniform stress distribution across the width of the section. Across the depth of the section, the stress varies linearly. Say this is a distance equal to y. This is the stress sigma. Okay. Similarly, at the bottom, a distance equal to y. So this is the stress in the opposite direction, which is compression. The top is tension, bottom will be compression. Remember that the bending stress varies linearly across the depth of the section. Okay. So This is for a solid rectangular section. This is case, we can say A. This is for solid rectangular section. Okay, this is the bending stress distribution. Okay. Now this is the section modulus, significance of the section modulus we discussed. Next, you take a hollow solid section. Hollow solid section. Let us see the bending stress distribution. See the beam, how the beam looks. Let me draw it neatly. This is the section inside. Okay. This is the hatched area is the material in the beam. The cross section will look like this. So that this inside dimension is a small b1. The outside dimension becomes small b2. So the inside depth is small d1. The outside depth is small d2. Okay. This is the hollow rectangular section. Anyway, the beam will go lengthwise. Okay. Now, this is the neutral axis. Okay. We have to find the I value about this. If the cross section is symmetrical, so this is one small section we are removing from a bigger section, so that we are getting a hollow rectangular section. Therefore, the moment of inertia for this section is given by I2 minus I1. This is the area moment of inertia for a solid rectangular section. That is I2 B2 D2 cube by 12 minus B1 D1 cube by 12. So once we find the moment of inertia, at the top layer we'll have a stress. This is the maximum bending stress. So here the material is there. So at this distance we'll have a minimum bending stress. Okay. So sigma max, the maximum bending stress is given by M by I into Y max. From this we can find the maximum bending stress. But what is Y max? Y max is D2 by 2. Okay. This is the distance Y max. Similarly, the minimum bending stress, sigma minimum, is given by M by I into Y minimum. What is Y minimum here? D1 by 2. Okay. Again, if this is a top layer under tension, bottom layer will be under compression, here we'll have a maximum tensile stress at top, and at the bottom we'll have a maximum compressive stress. Here we'll have a minimum tensile stress at this point, and at this point here, the point where I'm showing here, okay, we'll have a minimum compressive stress. So to draw the stress distribution, let us extend the lines. Okay. These are the construction lines. Now draw the reference line. Okay. Okay. Draw the reference line somewhere here. This is the reference line. Okay. See, top tension. This is the tensile stress. And it will vary linearly. Okay. This is the minimum tensile stress. Here at the bottom, because it varies linearly, this is the maximum compressive stress. Here, this is the minimum compressive stress. Okay. I'll write here sigma max compression. Here, this one, sigma minimum compression. This value is sigma minimum tension. Whereas this value is sigma max tension. Okay. Now in between, we'll have a sum value between maximum and minimum. Here also at the bottom, we have compression. Okay, it will be like this. So here, from here to here, there is no material, so no stress. Okay. So this is the stress distribution for a hollow solid rectangular section. Sorry, this is hollow solid rectangular section. Heading. Okay. So when a hollow rectangular section is subjected to complex loading, first we have to find out the bending moment M. Then by using this equation, we can find the moment of inertia about the neutral axis. Then we can find out maximum bending stress and we can find out minimum bending stress. Okay. By using these values. Okay. So the hollow sections will have advantage compared to the solid sections because inside we are removing the material where the stress is actually very small value, and we are keeping the material where the stress is high. Okay. So this way, the hollow rectangular sections will have a somewhat advantage compared to the solid sections. But the only drawback is the manufacturability. Now, circular sections. Circular solid section. Okay. Suppose, say here, this is the circular beam. You fix, okay, at one end, say this is the longitudinal axis called Z axis. Say this is the load axis, Y axis. This becomes our neutral axis, that is X axis. Okay. When this is, see, this is the load axis where you are applying a load. This is load P. This load P will create a momentum like this. Will try to bend the beam like this. Okay. So that we can find the bending moment. Say this is the distance L. P into distance, the load into distance gives moment. Okay. Now the top will be under tension, bottom layers will be under compression. Okay. Now the bending stress sigma is given by M by I. Okay. If I take into Y, if I take the circular section, this is the circular section, this is the neutral axis. Okay. Now here we are considering a small strip at distance equal to Y. So the moment of inertia we can find out about this axis. For a circular section, the moment of inertia is given by pi d to the power of 4 by 64. This is the derived equation from engineering mechanics knowledge. Okay. Now, the maximum bending stress occurs here at the top point where the distance is y max. Therefore, when sigma will be 0 when y is equal to 0, that is on the neutral axis. On the neutral axis, the bending stress is 0. Now, when y is equal to d by 2, where d is the diameter of the circular section. D is the diameter of the circular section. When y is equal to d by 2, the bending stress becomes maximum. Sigma max is given by m by I into y max. That is given by sigma max is equal to m by I into by y max. This we are calling as a m by z. Okay, where z is section modulus for a circular section. So that for a circular section, z is given by I by y max. That is given by pi d power 4 by 64 by d by 2. That is pi d cube by 32. Okay. So that the bending stress sigma max okay, I'll write here. Sigma max is equal to m by pi d cube by 32. Therefore, that implies sigma max is given by 32m by pi d cube. This is the equation to find a maximum bending stress in a circular section. Okay. Now let us see the stress distribution. For any stress distribution, we have to draw the reference line. Okay. Top is tension, and anyway the stress varies linearly. Okay. This is the stress distribution. So here we'll have a sigma max compression. Here sigma max tension. Okay. So in a circular section made of any material with any fixing condition, because in this case I have shown a cantilever structure, okay, which is subject to loading, we can find first the bending moment, and we can find the moment of inertia, we can find the section modulus, then we can find the maximum bending stress. Okay. So where the maximum bending stress occurs, where the moment is maximum. So the moment will be maximum at the fixed end here. See, at this point here, this is the point A. Okay. So the stress here will be, if you show the stress on the structure also, it will be like this. This is center. It will decrease like this. Bottom will be compression. Top will be tension on the structure like that. So this way we can find out the bending stress anywhere across the length of the section, because if the moment is given as a function of load P into X, then what is sigma max? Generally m by I into y. That is, m is px by I into y. I can write even bending stress in this format also. Okay, by standard format. See now, where x indicates the distance along the length of the structure. Say at fixed end, x is equal to 0. At the free end, x is 0. At the fixed end, x is equal to L. Okay, we are moving from free end to the fixed end. So when x is equal to 0, even the y is not 0, the bending stress will be 0. That means at the free end, the bending stress will be 0 when the beam is subjected to transverse load. Where y is the depth across the section. Okay, so even though when you take it at the fixed end here, x is maximum value, but if you take on the axis of the beam here, from the fixed end here x is maximum, but y is 0. That's why here the bending stress will be 0. Okay, this way they can ask you anyway, say n x is equal to L by 2 here somewhere. X is equal to L by 2. Say across the depth, say like y is equal to, say like d by 4. Somewhere here, they may ask you to find the bending stress, which is normal to the cross section like this. Or at the bottom somewhere here, at a distance x is equal to L by 2, we can find out the bending stress, which is a compression like this, opposite direction. So that the bending stress will again vary linearly like this. So by using this equation, we can find out the bending stress for a given beam along the span will be taken care of by x, along the cross section by the distance y. Anyway, I is constant and load is constant. Okay. If the load is again different, like distributed loads, again the load also will be a function of the distance. Okay. So this is the solid circular section bending stress calculations, and this is the bending stress distribution for circular section. These are the equations. Next, we'll say hollow circular section. Hollow section. Say, let us consider a hollow section. Say like this is the neutral axis. So here the material is present. This is the material. Project the lines. Okay. Draw the reference line. Now let us see here. When this is subjected to a bending moment, M, like this, top will be tension, bottom will be under compression. Okay. Now, the I value for this is given by, because the hollow section is nothing but, if you remove the smaller section from the bigger section, we'll get a hollow section. Say like this. This is one solid section, bigger section of diameter D2 minus there is a one more small solid section D1. This will result into the hollow section, which I am showing here, like this. Okay. So that if the diameter of the smaller one is D1, bigger one is D2, then the moment of inertia of the bigger one is I2. The moment of inertia of the smaller one is I1. Subtract the smaller from the bigger because both the sections got the common axis. If the axis is common, we can subtract or add the moment of inertia. That is I2 minus I1. That is equal to pi d to the power of 4 by 64 minus pi d1 to the power of 4 by 64. This is the I value. Generally in the numericals, the smaller diameter D1 will be given as a fraction of bigger diameter. Okay, where d1 is the smaller diameter, d2 is the, where k is a fraction always less than 1. Okay. Generally, it will be like a 0.6 or 0.5, 0.7 like that. Okay. So that now the I value becomes pi by 64 d to the power of 4 1 minus k power 4. This is the high value for a hollow section, where d1 minimum diameter, d2 maximum diameter. Okay. Then sigma is given by, the normal stress is given by m by I into y. Okay. So when y is maximum, sigma will be maximum. Therefore, sigma max is equal to m by I into y max. What is y max? d2 by 2. Y max is d2 by 2. Okay. Then the minimum bending stress occurs at the lower portion here. Okay. The maximum bending stress occurs at the top portion here. Okay. Sigma minimum is given by m by I into d1 by 2. Okay. So in these cases, y minimum, wait, you write here y minimum, so that y minimum is given by d1 by 2. Okay. If you take the ratio of the stresses, maximum stress to that of minimum stress, it only depends upon the diameters, d2 by d1. Okay. This is the equation. This is for finding the minimum bending stress. This is the equation to find the maximum bending stress. Remember these values so that we can solve the numericals. We can find out the bending stress across the width of the section, across the depth of the section, along the length of the beam. Now let us see the bending stress distribution. The top is compression, tension up to this much. It will vary linearly. At the bottom it will be compression. Okay. It is like this. Here in the opposite direction. This is sigma max compression. Here, top, sigma max tension. This much value. Okay. Now this value is sigma minimum tension. Whereas this value is sigma minimum compression. Okay. This is the bending stress distribution for a hollow circular section. In some literature, okay, they are showing this stress distribution in a different style. Okay, that also correct. Let us see how. See, anyway, top is tension. Okay, bottom will be compression. Okay, you can show both on the same direction, but for tension, the arrow will be outward like this. For compression, you can show the arrow inwards. Okay. Got it. Both are applicable. The bending stress distribution for a hollow circular section, applicable. We can draw this way or we can draw this way. Okay, both are correct. Okay, because stress and load, they got actually direction. So based upon the law of transmissibility, you can show in the same direction anywhere. So that's why both are applicable. This is for hollow circular section. So we discussed the Flickr equation derivation, followed by the Euler assumptions. Then we derived the equations for solid rectangular section, hollow rectangular section, okay, solid, hollow rectangular sections, and stress distribution I given, and the respective equations I given. Then we discussed the solid circular section, solid hollow section, and the corresponding equations and stress distributions we discussed. Okay. Now we have to go for a numericals. We have to solve some numericals based upon the Flickr equation of bending for solid sections, hollow sections, both rectangular and circular sections, solid as well as hollow. Besides this, we got some more economical sections are there, like I sections, where it is I section. This the beam can, so the lengthwise the beam goes this way. This is the I section for the beam. Okay. This is I section. So here in this I section, this is bottom flange. Whereas this is top flange. Okay. If you join them by vertical member, this member is called web. Okay. This is the I section. Like this, we can have a different sections. The purpose of these sections is to increase the section modulus, so that to increase the geometrical strength of the material, like given material, by distributing away from the axis of rotation, so that the bending stress will be less in the beam. When the bending stress is less, the beam life will be very high. Okay. Now, if I change the flange orientations, okay. Suppose if I remove the bottom flange, the beam looks like this. This is called T section. Okay. This is the T section. Right? T section. Only will have a top flange. Or if you remove the top flange, it will becomes inverted T section. Okay. This is the I section. This is T section. In the numericals, they may give like any kind of cross section. Okay. Suppose if we keep the flange only one side, so this is C section. This is C section, or also called as a channel section. Okay. For this channel section, if I top flange or bottom flange, if I change the the location into the opposite direction like this, this is the Z section. Lengthwise, the beam will go like this. I'm not showing the entire length. Okay, I'm showing only portion of the length. This is the Z section. Okay. Now here we got some significant here. See, this I section is symmetric about centroidal Y as well as X axis. So this is the section which is symmetric about both axes. This is symmetric about both axes. Okay. Whereas the T section is symmetric about vertical axis, but it is not symmetric about a horizontal axis. So somewhere the center of gravity will be here. So this is unsymmetrical about the x-axis, symmetric about y-axis. But if you see the channel section, this is the symmetrical centroidal axis. Okay. Right? But the centroidal y-axis is not symmetrical. Whereas this section, see, this is centroidal x-axis, this is centroidal y-axis. So this is opposite symmetry. Opposite symmetry. That's why this is also called as a skew symmetric. Skew symmetric. Okay. Now, see, this is the first kind of sections where the cross section will be symmetrical about both the axes, like circular sections, rectangular sections, or I sections. Now the T section, which is symmetric about one axis, unsymmetric about x axis. So whereas the channel section also symmetric about x axis but unsymmetric about y axis. Whereas the Z section, it looks like a Z. That's also called as a Z section, or like a skew symmetric, or you can say anti-symmetric, also called as a anti-symmetric. If you refer different literature, they will call by different names. So now there is one more section which is unsymmetric about both the axes. Okay. This is unsymmetric about x as well as y. Okay. In the entire structural mechanics field, engineering applications, we'll come across sections which are symmetric about both axes, sections which are symmetric about y-axis, unsymmetric about x-axis, or symmetric about x and unsymmetric about y, or anti-symmetric sections, or unsymmetric about both axes. So the only problem in this kind of sections is, so you must know how to find the area moment of inertia of that section for a corresponding centroidal axis. Okay, that's why for this B and C sections, these sections here, first we have to locate the center of gravity. Then only we can find the moment of inertia about centroidal x or y axis. For this, you can locate directly. Here also for the L section, this is L section. We have to first locate the center of gravity, then find the moment of inertia about x and y axis. Depends upon the direction of the loading. So the section undergoes rotation, the beam undergoes rotation about a particular axis. On that axis, we have to find the area moment of inertia. Okay. These are the various economical sections which are used in the structural mechanics field. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.